Okay, good afternoon, everyone. My name's Eli Dart. I'm from ESNet, and I'm going to talk a little bit about, oh, is this like not, is this thing on? So I'm going to talk a little bit about where I think where we've been, kind of where we are, and where I think we should be going, sort of from a strategic perspective, in terms of being able to support the science collaborations that we all support, and what I think it means we all should be doing as a community together. So if we look over the past little bit, and we sort of look at what we've done, I think we should actually be really proud of ourselves as a community. So we've done a lot of stuff, and we've actually done a pretty good job of it. So I'm going to take this view sort of from the center going outward, right? But so science networks are now what I like to call big, fast, and clean, right? So to first order, the national backbones are all, they all function well. This includes the connections to each other at RNA exchanges and private peerings both. This includes campus networks and international circuits as well. This is all to first order. I mean, it's not like there's never problems. We all know that there's still problems to fix, but to first order, people can make the assumption that this stuff actually works. It's well built and it's properly configured. We've instrumented those networks for performance, right? So perf sonar is deployed largely ubiquitously. What that means is that we can both ensure that things are operating correctly, and when a problem does arise, we can localize it and we can fix it with relative ease. Certainly compared to 10 years ago, things are fantastically better. We've deployed science DMZs at the edges of those networks. This is true in campuses. It's true for individual experiments. It's true for national laboratories, supercomputer centers, right? So we've got now a network core, a ring of science DMZs around the edges. We have DTNs deployed in those DMZs, right? And that connects then the storage at the sites or the experiments at the sites to all the other things on the other side of that network. And then data orchestration platforms that run on those DTNs that allow this whole giant distributed thing to be effectively driven by a scientist in a useful and productive way. So if I was to be a network nerd and draw a diagram of it, this is what it might look like, right? And that's all great if you're a network nerd. But not all of us are network nerds, and so lots of us do draw these sort of stack diagrams of things, right? Where there's this lower level substrate, right? And then there's science DMZs on top of that and DTNs on top. But that diagram doesn't really capture it either, I don't think. I like this view a little bit better. And so if you think about this now, you've got a network core in the middle, a science DMZ ring on the outside of that, DTN ring on the outside of that. The reason that the data orchestration platform is a different color is that's the only thing the scientist should have to reason about. Everything inside that pink ring, and yeah, the color's terrible, okay, sorry, but it's supposed to be contrasty, right? So it contrasts. So everything inside that ring, I, as a scientist, should not have to reason about in order to drive this thing effectively. Now, there are some user bases that want to reason about and are good at reasoning about the entire infrastructure all the way to the core. And we have ways of accommodating those users. They do very well at it, and that's great. Yes, I'm talking to you, LHC experiments, right? And that's great. And they can do that, and they should do that. It's productive for them. It works. But for most of the other science collaborations, that's not the way they want to reason about cyber infrastructure. So unfortunately, we're not all the way there yet. So I just patted us all on the back for something that's not actually fully realized. I would argue that there are three major tasks that remain. One is we need to finish the deployment of that interoperable platform across all the science DMZs. And that's not just deployment, it includes test validation, right? You wouldn't deploy a cluster, just plug it all in, turn it all on and say, okay, work now. Right? So no, you have to actually integrate it. You have to actually make sure it works. You have to actually iron out the kinks. So that's fine. So I would argue that's sort of partially complete. The other thing we have to do is integrate the major sources of scientific data with this larger platform. That has begun, and I'm going to talk a little bit about that in a minute. And then the last thing is we've just changed the way in which scientists might access cyber infrastructure. So we have to teach them about these changes that we've made to the world that they live in to allow them to use it effectively, right? Because if we go and do this thing over here and we don't tell anybody about it, we don't teach anybody about it, they're going to still use rsync over SSH like forever, and that's unfortunate. So let's talk about that platform for a minute. So as I said, right, it's partially done, it's partially complete. There's still more to do. There's a set of features over time that I think are have sort of risen to the top as things that are actually really important about this sort of thing. One's the ability to automate, because data sets scale, I don't, right? And if the rest of you do, if there are any exponential people in this room, that's awesome. Why don't you raise your hand and teach me how, because I could really use it. I am not an exponential person. And so, you know, we have to be able to automate our way out of these things. Speaking of automation, we need automated fault recovery, because life is short, and no, I don't want to dig through all 5,000 files to see which one didn't transfer. Data integrity is a major issue. Integrity validation between source and destination, so that you know that the file that got sent is actually the file that got there. And then we need to be able to integrate it with the tools that the scientific community uses to find and consume data sets. Now, there's a bunch of different examples of platforms. One that a lot of people are familiar with is Globus. Another that people are familiar with is ecRootD. This is used as the backbone for a lot of what the LHC experiments do. They move ridiculous amounts of data with ecRootD. The OSG stack is also used by a lot of folks. The examples in this talk are based on Globus, but there are several of these platforms out there in the community. And as I'll come back to this point a little bit later, but I think it's important, so I'm going to say it now. The scientist has to not be made the integrator for all of this stuff, right? If we make the scientist the integrator, they're going to use rsync over SSH forever, and it's going to perform badly forever. And we really need to get out of this. But this is something the scientists can't do for themselves. And I'll talk more about that in a little bit. But if you get the platform right, this is what you get, right? So this is some work that we did a year or so ago between the 3 DOE supercomputer centers and NCSA. Those numbers are minimum, average, and maximum in terms of data transfer performance in gigabits per second between those two endpoints. And unfortunately, I can't read it, so I'm guessing you can't either. This down here on the right is the composition of the test data set. So this is not a benchmark-friendly data set. It's a bunch of data that I got from an astrophysicist. This is part of a big astrophysics simulation. So it's what, 19,000 files, a couple hundred directories. It's about 4.4 terabytes in size, and the file size ranges from 0 bytes up to on the order of 10 to 11 gig per file, right? So this is not a benchmark-friendly data set at all. This is what real people need to move around when they need to sling data sets around between supercomputer centers, right? But when we started this project, a bunch of these performance numbers were single-digit gigabits per second, even though there are 100 gig pipes interconnecting all of these things. I mean, the paths between those supercomputer centers are 100 gig clean all the way. And so we took it from single-digit gigabits, whatever. Some of these are over 50, right? So, and this is it's a routine use of a production system. You know, Eli going clicky clicky on the GUI, right? It's like it's as dumb as you can get, and it works, right? So this is what happens when we get it right, and this is something that all users of those facilities can just use. The underpinning, right? The underpinning architecture, if you will, of this thing is this aspect of the Science DMZ design pattern, right? So in particular, it's the storage system at that supercomputer center, front-ended by a DTN cluster, right? And it's all derivable directly from that. So I mentioned science data portals a moment ago, and so what is a data portal really? So it's a collection of scientific data relevant to a particular field. So maybe it's climate data, maybe it's a sky survey, astronomy, cosmology, whatever. Maybe it's a bunch of genomes, maybe it's a bunch of material science data, right? There's a whole bunch of these things. out there in the scientific community, and they provide a bunch of services to scientists, right? So I can go search for a data set that's relevant to my research. I can go access that data if I've got permission to do so. I can download it. I can do whatever work I need to do with it. The interesting thing about these, though, so it's access via a web server, right? Well, a lot of these were designed Y2K or so, something like that, right? And so what does that actually mean? So back in the day, for those of us who remember back in the day, you got data like this via command line FTP. And you would FTP, whatever, and you got this little thing that looked an awful lot like a Unix shell because it was an awful lot like a Unix shell, and you would ls and you would cd and you would type around just like you were on a Unix shell. And then there were some commands called get and put and things like that that would allow you to either place data on the server or download data from the server, right? And that was the state of the art at the time, and it worked fine, except that you can't search it effectively, and there's some other thing, incorporation of metadata and things like that was actually kind of hard. And so around Y2K or so, it was like, okay, well, the Apache web server is kind of nice and stable at this point. CGI programming is around, that's actually pretty good. Database integration's gotten okay. Well, okay, so that means now I can take the metadata from my data set and I can stick it in a little database. And I can use CGI programming to generate a set of web pages. And somebody already wrote a GUI for me. It's called a web browser. So me as the portal developer, I don't have to do that, right? I can just set up this web server thing and somebody else handles the GUI, and presto, there's now this nice human-friendly searchable GUI for my data set. And oh, by the way, I can give the web server a file system mount pointing at all the same data objects that my FTP server is serving up anyway, right? And so that makes all kinds of sense, and that's great. But those things haven't changed in a while. Now, I'm going to show you an example here of where we'd like to be. So I'm going to talk about sort of the better version of data portals like this in a moment, but for demonstration purposes, I'm going to show you what an example looks like. So I'm going to look at the Research Data Archive at NCAR, and this is what the Research Data Archive at NCAR looks like. It looks like a web page, right? So I want to find some data. Let's go look at the data sets that are on here. Right, I wonder what type of data I want. I'll get some grid data, junk, okay. And so there's all these data sets that are available on this thing, right? And so maybe I'll grab this one. And so here's a whole bunch of the metadata I was talking about, right? Here's the time, there's the time range for it. How often is it updated? It's updated irregularly. I wonder what that means. If I were a climate scientist, I might know. So if I wanted to cite the data set, right, there's all the information necessary to provide a citation for the data set if I use it in my work. There's the size of the data set. It's about 0.5 terabyte. And it's in NetCDF format. This should surprise nobody because most Earth system data is in NetCDF format. And so, okay, so I decide I want this. Okay, so there's a data access button here. Now, I could do it the bad old way. And I see that thing that says web file listing over there. What that gets you is page after page after page of little links that you can click on to download individual files. And so if I want to be really, really bad and mean to my grad student, I can say, go click on all of these, please, and tell me when you're done with all of them and verify that they all came down correctly. Or I can use the sort of modern platform idea, and I can click on this other thing. What it does now is it pops up a Globus job with the entire data set on the left-hand side. So give me all that. Wow, and the resolution on this screen is really tiny. So I'm going to now transfer it over, and I have an account at NERSC. All right, so the other thing is I'm pulling down 0.5 terabyte of data. Maybe I don't want to analyze all that on my dinky little laptop. Right? And so what I want to do is orchestrate the placement of that data set at a supercomputer center where I have permission to run. And so, okay, here I am. And no, I don't want that. Boy, the screen is so tiny that I don't have the create directory link. Ha, ha, ha. Okay, well, let's drop it over here. And we'll kick it off. So that's all fine. So what have we actually done, right? I just showed you the new way. The old way, remember, is our legacy thing, which is all running on a web server someplace, stuck behind whatever it's stuck behind. And if I say, okay, I want to increase the performance of this thing, so what do, right? I'll stick it in a Science DMZ, right? No, you don't. And the reason for that is, what is that data portal application really? It's a database-driven web services application. Now, what's the really nice, tasty, juicy target for security exploits? Database-driven web services applications written by grad students 15 years ago. Yeah, okay, no, stop. So what we don't want to do is put that in a Science DMZ where all we have to defend it with is ACLs. Okay, that's a poor match between the security policy that you should have for your Science DMZ and the type of application that you would be deploying in your Science DMZ. Okay, I would totally not recommend that. And so we have to think our way out of this. So what are we going to do, right? Well, can we change the architecture of a data portal a bit and perhaps think our way out of this? So I'm going to give you an example of what that kind of architectural change might look like by looking at CDNs and what CDNs did for the commodity internet. So what does a content delivery network look like, right? So this is, say I'm Airbnb, right? So Airbnb has all these beautiful pictures of the place that you're going to vacation in. They're delivered very quickly to your phone, and that's all very nice. The way they do that is this big cache push of static content out to the edges of the network, right? And that's not where the complexity is, right? The complexity is in the dynamic content. And so if we can separate these things out now, right, maybe that's a big win. So the way it was before we managed to do this was you had a web server someplace, and I'm sure we all ran these, and all the content was stored there, dynamic and static. So when you go and you download that thing, you now pay the price of whatever the path happens to be for all the large-scale data objects as well as the dynamic content, right? The dynamic content is typically small, but big images take a while to come down. You don't get as nice a user experience, right? And so, okay, so is there a different way that we can do this? Yes. So you take apart the traditional web page, and when you have references to large static data objects in that thing, it doesn't point back at the web server, it points to the big cache over here that's out next to your phone. And so then when you download the web page from your phone, right, it comes straight out of the content delivery network's cache, and your browser is none the wiser, right? So you just simply see increased performance, right? From your browser's point of view, there's just a web server on the other end of the net, and it doesn't really matter. Never mind that this is what's actually happening behind the scenes. So we haven't brute forced our way out of the problem. We haven't given everybody 10 gig to their phone. Right? What we've done is we've changed the underlying architecture of how web pages are delivered, right? And that gives us a significant performance gain. So I'm not advocating CDNs necessarily for scientific data. There are some folks whose data sets are amenable to that, some where it's less amenable to that. But the idea is to examine what a data portal looks like from an architectural perspective and see if we can change it in a way that makes more sense, right? And makes it perform better and be more scalable. So what are the functions that we want in a data portal, right? We want search and we want to be able to query it. We want to look for data sets. We need a method for data access, both that is consumable by humans and that's consumable by machine. Because remember, we want to be able to automate to this. I don't want to go grab 5,000 data objects by hand. Thank you very much, right? So it was really nice would be to do what I just did with that NCAR data portal, right? I browsed it with my eyeballs, and then I said, oh, okay, well, here's the stuff I want. Please automate that for me. So if you look at then what the performance pain is, it's primarily in handling the transfer of the large-scale data objects, right? It's orchestrating that transfer from wherever it is to wherever it needs to be. And so can we take that apart? Well, the answer turns out actually to be yes. So what we do is we take this thing, which is our legacy model, and we apply the Science DMZ model to it and say, okay, instead of the web server handing out pointers to data objects that point back at the web server itself, it points at a DTN cluster in a Science DMZ over there. That DTN cluster is arbitrarily scalable, right? You want it to go faster? Add more DTNs to it. The naming doesn't have to change, right? literally just add more. And if you want to grow the file system, you can grow the file system. Nothing else has to change. There's actually a paper there which describes this design pattern if you're interested. But what we've actually done is significantly change the architecture of a science data portal in a way that makes it much more scalable. And NCAR is not the only one. The DOE's Joint Genome Institute is also implementing exactly this for large-scale download of large data objects. And so why would we want to do this? Well, some of the reasons to do this are just sort of Moore's law type scalability. Right, so the number of data objects has gone up by a couple orders of magnitude in the past 20 years. The size of the data object has gone up by a couple orders of magnitude in the past 20 years. And so, I mean, there's just a brute scaling component that means, you know, the old model is kind of getting old and tired. But there's another thing too, which is the way people are using high-performance computing facilities now is very different from the set of assumptions used, the design assumptions under which these data portals were put together originally. And I would say, I mean, it's pretty obvious on its face, but it bears repeating. You can do a lot more with the supercomputer center now than you could 15 years ago. I mean, I remember when the first teraflop machine was deployed at Sandia National Laboratories in the late 90s. Right, a whole teraflop, right? And it wasn't that long ago, folks. So, you know, exponentials get us some interesting places fairly quickly. So if we can retrofit data portals to make them more useful for that, then we can get to other things like this. So here's a couple of applications that illustrate this. So this is the first exascale application run. This was on the initial delivery of the Summit supercomputer at Oak Ridge last summer. And what is it? 1.8, I think? Yeah, 1.8 exaops on this thing. They did subsequent runs and I think got it over 2. But 1.8 exaops. And so this is an analysis of genomics data. Right? Here's another one from a couple years ago, which is using machine learning to identify atmospheric rivers in climate model data. Now, the thing that's interesting about this is a fundamentally different analysis paradigm than the one for which the legacy data portal was designed. So they want all the data that matches a given set of criteria which exists in the field, or all the data which exists in the field that matches a certain set of criteria, right? And in order to do that, they need to be able to get at things in a way that it doesn't make the assumption that the old data portal makes. So the legacy data portal model makes the assumption that it's impossible to deal with all the data. So I'm going to make it easy for you scientists to get your hands around just the tiny subset of the data that's relevant to you right now, and you can put it on some kind of personal computing device, whether it's the nice workstation on your desk or the laptop in your hands, and you can do whatever it is that you need to do with it. And that's fine for that use model, but that's very different from, I want to collect everything onto a big supercomputer and grind it through whatever my best machine learning techniques are. And so, I mean, those data portals were great. They're just a product of their time, right? From the perspective of those data portals, we're living in the future. From the perspective of today, those data portals were designed in a dim and distant past. And so we have to do better. And so the idea that somebody's going to want just a tiny subset, that's no longer a reasonable assumption to make, right? They want all the data, and we should be able to give it to them. So looking at the NCAR RDA, here's some performance benchmarks that I did using actually a different data set. Actually, let's see how we did. How did we do? Okay, so while I've been here yammering at you, that data set came down in about 6 minutes at over 1 gigabyte a second. So 0.5 terabyte in 6 minutes. Right? No human intervention required other than clicky on the GUI, right? So that's what we need to be able to do in the general case. right, to support the scientific community for doing this kind of work. Now, I would argue the scientific community can't do this on their own, right? They need our help to do this. And there's a couple of reasons for that. One is they don't have root on everything that we have root on, right? We certainly don't give scientific users root on ESNet. And I'll bet you don't give them root on your campus networks or on your supercomputer resources either, right? And nor should you, because in fact, they don't have the expertise to do that, and they don't want the expertise to do that, right? They want to use a thing that's productive that allows them to do climate science or biology or astrophysics or whatever it is that they need to do. And so we, as the community that owns this collection of cyber infrastructure resources, this is stuff that we have to do, and then we have to teach the scientists how to use the new and better thing, right? And so I would argue this is the path that we must walk. And I just mentioned this, it bears repeating, networks can't do this alone either. I think that the networking community has a key role to play, both as the people in the middle who can see how all the different pieces at the edge interact, but also as a neutral third party, because we've all been in the performance situation, right, where two organizations are pointing at each other saying, no, it's your problem, right? So as a networking organization in the middle, we have the ability to mediate between the different parts of a science collaboration or of a troubleshooting issue. But we don't own the supercomputer centers. We don't own the data portals, right? Those folks have to do that themselves, hopefully in collaboration with us so that we all get the architecture right, we all get the design right. So that's the vision, right? And I would argue if we can get to that place, and we're partway there now, and we're partway enough that we know it works, we can really change the world. And so what does the path forward look like, right? The path forward looks like we need a bunch of DTN clusters fronting all the things, right? And we need a platform deployed on those DTN clusters that interoperates across all the things, whether it's a particular experiment, whether it's a data portal, a single lab belonging to a scientist, whether it's an HPC cluster at a university, whether it's a national HPC facility, like something in DOE or NSF, right? Whether it's the LHC experiments, right? All of this stuff needs to be able to talk to each other in a way that's scalable and drivable easily by humans for useful purposes. So this is how we're going to move forward, and this is how we're going to solve all the problems that are so important to humanity right now, right? So there's a bunch of stuff that humans need to figure out, right? We have this little problem called cancer. So it turns out that's a gigantic data analysis problem, right? And we're nowhere near scaled to the point where we need to be in order to solve that effectively. We have an energy infrastructure that we need to rebuild. We need fresh water resources that we need to find and understand and deal with, especially here in California. Remember that drought 5 years ago? There's another one coming. I don't know when, but it's coming. We got to figure this out. So there's a bunch of different things, all of which need large-scale computing and large-scale data analysis in order to figure out. Right, so Isaac Newton said, if I've seen further than others, is because I stood on the shoulders of giants. Okay, the large-scale data sets accumulated by the scientific fields that we have today, those are the shoulders of today's giants. Right, those are today's giants. If we can give our scientific community the ladder to climb up, they can now do the work that we need them to do and solve all these problems for the good of us all. Right, and I'm speaking big here. This is not hyperbole, right? This is for real. This is what we need these people to do, and that's how people in this room and in this community can help make this stuff happen. And at this point, it's not a design problem, right? It's not some theoretical debate, right? We know this stuff works. We have the model. We have the technology. We have actual deployments that actually work in actual production, right? We know this stuff works. All we have to do is actually do it. So, thank you. Comments, questions, fruit, rocks, rotten tomatoes. Jeff. Oh, where's the mic? Right here, Jeff.
Yeah, so Jeff Weekly, UC Merced, and we're maybe contemplating violating one of your design practices and putting a database on our Science DMZ. But I wonder if you have any opinions about running some of these sort of almost microservices on the Science DMZ, but in a container that sort of firewalls it off and segments it off and limits it.
So I mean, so that's going to be that's between you and your security officer, right? So some of it is how much can you trust that service to defend itself, and if you open that service up, how much does it add risk to the machine that hosts it? And so one of the sort of central pieces of design leverage that the Science DMZ has is the limitation of the services deployed on the systems there. Right, so for example, those Globus DTNs that I showed, that's all they run, right? They're not running web browsers. They're not, user desktop machines. Right, and so if you have just a particular service that speaks a particular API, and that's what it needs to do, then and it is such that it needs the performance acceleration that it would get from being in a Science DMZ, then sure, deploy it. I mean, the point here is to be fully cognizant of what you're doing, right? I mean, in a lot of cases, the thing that catches people out is when something gets deployed and people don't know what's there, and so it's not professionally maintained, it's not patched, right? Things like that. If you've got something that's professionally maintained by a competent operational team, and it's narrowed down to where that's the only service it provides, and that's the thing that you need, right? Then yes, by all means do it. Because remember, right? If you stood that thing up behind a firewall, right, the packet filtering policy would be the same. It would still be let all the things in the outside world that need to access this thing, right? It's just how you choose to implement that policy, right? And Michael's going to get into Science DMZ security a bunch in the next session, so we can dig into that sort of thing in more detail if we want to. Other questions? More Rotten Tomatoes. Yes?
So I'm actually contemplating building a research background on my campus.
Mm-hmm.
Certainly put a DTN at the edge going off the CENIC. I have a number of labs. There's the bio lab and there's Peter Deutsch, Cal Poly Pomona.
Mm-hmm.
So we're definitely going to have a DTN at the edge. So the question I've got as I looked at your architecture is, there's talk of individual DTNs in individual labs as well, labs where there's a fair amount of data. Is that all part of the same concentric ring, or is there layers of the DTN? So,
yeah, so I didn't get into, I didn't sort of do a deep Science DMZ architecture dive in this talk. I have other slides on the laptop. And so maybe we should talk afterwards, but you have a lot of flexibility in how you can put that sort of thing together. Depending on, so if your campus is fiber rich, you can just pull dark fiber out to each one of those labs and make a little Science DMZ for each lab, potentially then each with its own security policy and its own security policy enforcement mechanism if you need to, which gives you a fair amount of flexibility actually. If instead you want a centralized service where they push all their data out to a big central file system front-ended by a DTN cluster, and you do all the access management via the DTN cluster, that's another way to do it. So there are a variety of ways you can do it depending on what works for your environment. And so, I guess I would say just think through how you want each one of those things to be used, how easy each of them are to manage. So, if it's a bunch of biology grad students in each one of those labs, do you trust them to run the DTN? Maybe you do and maybe you don't. And so maybe it would be better if there was a centrally run data service that they got to put stuff in so you didn't have the internet banging on their door, right? It all depends, right? So these are socio-technical constructs, right? You can't ignore the human part of it.
Yeah, and our biggest issue is the funding issue. We don't have the people to run the central stuff and to staff it. I think we're going to be pushed to the edges and let the grad students do it. Separate issue, and I'm waiting for the next talk. So.
Yeah. So there's more in Michael's talk about exactly this sort of thing. You bet. Others? Yes, no, maybe? No Rotten Tomatoes? I was all ready to catch them. Okay. Thank you all very much.
Round of applause. Thank you very much.